how it works, except to say that it's simple, easy to use, and it works, and you'll be able to grab it off the web if you want. And it's so simple that the inverse square law is actually right here. There's r times g times m1 times m2 over r cubed, which becomes the inverse square law. And the reason it's great is it's so simple you can audit it. There are a lot of other programs that already do this, but it's hard to check. Whereas here, it's just the force between a bunch of point masses.
It doesn't look like a r squared force.
There's an r over here, and then there's an r cubed over there. Yeah, because I need to get a vector valued thing out at the end.
Well, that was close.
If the questions are like that, then it's going to be okay. So now we're going to get into the part where I'm going to get more questions, which is data analysis. So this whole project is completely reproducible. So there's a Git track repository. I'm resolving some licensing stuff right now associated with the GPL because I'm trying to figure out exactly how I want to license this stuff. But I do want to make it available. If you have a SEMPA GitHub account, you can already jump in and go see the code. It'll be out soon, just as soon as I figure out what's going on licensing-wise. And there's a single command that builds the thesis from raw data to the end. So a while ago, Matt Sternberg and I hit go, and then now there's this thing on the USB stick, and I didn't do anything in between, except we did watch to make sure that nothing broke. You can audit all of it because it's procedural, and it makes it possible to do really hard stuff. And make sure that you know it works every time you do it. So what do raw data from this experiment actually look like? So this is actual real unblinded data. This is the first 8,000 seconds of science. And so the attractor position is here, and I can explain the spikes later if you want. Down is closer to the attractor, or to the pendulum. So it moves in blocks of what we call 10 switches, which are then lumped into a cut. And I do all my analysis on these cuts. This is the torque. And so you can see that there's no obvious apparent structure that looks like this up there. So you've already tested the inverse square law by eye by looking at this plot. And then these are the Fourier spectra. So this line out here is my injected gravitational signal. If there were an inverse square law violation, you would see it sort of straight above this guy, which is right in there. And the reason it has funny structure is, of course, this is a Fourier transform thing that's sinusoidal. It's kind of a structure. So when I went to say, okay, Jens, I've got all my analysis together, time for you to check it. I gave him 20 pages of stuff, and he looked at it and said, I don't know how that works. Please give me a flowchart. This is a flowchart, and that's way too complicated for me to explain to you right now. So I'm just going to explain a couple of things. I'll tell you about this filtering thing that I did, which I gave a Monday meeting about, and everybody went to sleep, but I'll give you just one slide. And, then I'll talk a lot about how I bootstrapped a bunch of fits, which is essential for you to interpret the unblinding for yourself. So all of our experiments are normally run by you take some data, and then of course it has all kinds of structure from the free pendulum oscillation and drifts and all kinds of stuff. So we normally run a filter through the data that knocks out just the pendulum behavior, we take out some linear drift term, and then fit for signs and determine some output value out of all of that complicated stuff. And so that amounts to being a complicated filter. And I opted instead to have one complicated filter whose properties I understood completely. There's sort of two sides of the same coin, but this is that filter. So this is I take a filter whose frequency response looks like this. I run it through the data. The fact that the response is low at low frequency means that it's a high pass filter. All the drifts get chopped. And then I have these calibration lines, so I need to notch them out and then retain my science frequency, which is not so far away from the calibration by design. And then there's, in torque units, the autocollimator noise gets worse at high frequency, so then I just do some low passing. So all that's built into one filter, and you look at a filter like that and you're like, that's crazy, I have no idea if that's gonna work. So this is a thing where I took a magnetic coil that couples to the pendulum through its magnetic moment, and I wired it up to the output of the pressure gauge that determines the attractor's position. And so then I can valve off the actual attractor motion and then figure out whether or not I can recover what I ought to be seeing when I ask the attractor to move. And so I've injected this big, or comparatively big torque for me, and then the solid blue line here is the average of the response over a bunch of time, and you can see that there's some transient business, and then things chill out, and then it switches, and there's some transient, and then it chills out. And so I only take data off the ends of these guys for each of these sets of switches. And so what did I actually do with the attractor? I moved it around in a lot of different patterns. There's a lot of what I call random attractor motion, which is great for teasing out systematics like one we had in 2007 that was at exactly our encoder grading spacing. So every 25, we've been doing 50 micron switches and 25 micron switches and 100 micron switches, and everything was great. And I tried 25 times pi micron switches, and everything was crazy because we had a 25 micron grading encoder, and we had no idea. So after that, I became orthodox about doing this because I wanted to see whatever was actually under the hood. And then I did a bunch of systematic tests, largely with square wave switches because it allows me to do some alternative analysis as well as random motion. So Jens told me not to put this slide up, but I wanted to show you that it is possible to plot what the raw data coming out would actually look like. But these are very hard to interpret by eye. It would take me at least 5 minutes to teach you how to read this plot. So it does exist, and you can do it. But I won't actually be showing you large compilations of raw data, precisely because this is an inverse square law violation, and that's definitely not. And it's hard for you to tell from here. So I did this alternative thing where I just looked at all the square waves. So everybody who's interested in numbers will get interested here. So I applied a bunch of different systematic effects. I applied a magnetic field, I increased the temperature of the attractor, I applied a temperature gradient across the attractor, and then I looked to see if there was any difference between that being applied and running with nothing, because I can do that blind. I can look at the differential measurement. And these numbers should be scaled down by about a factor 10 in order to make them, to scale them to the actual operating conditions. And 0.1 femtonewton meters is the scale of interest. If it's below 0.1 femtonewton meters, I'm good. And if it's not, then I might have to worry at least a little bit. These thermal effects were scaled by at least a factor 10. So this one actually winds up being at about 0.5 femtonewton meters. And I'm excited to see whether or not my more complicated fitter picks up that same effect. And then this I'm particularly proud of. This is when I turn that pneumatic actuation valve off, I don't see anything. So the attractor doesn't move, I see nothing for sure, which is great. Didn't have to work out that way. And it's the reason I didn't hammer it down to 0.1 is that this is a thing where you can't make the effect any bigger. You can just turn it off. So you'd have to measure for as long as I took the entire science data set to make that go away completely. Okay, so how many of you have ever bootstrapped data? One person. I've already converted to the cult. So my purpose here is not to evangelize bootstrapping as an analysis technique. I just want to show you what I did, and you can decide for yourself whether or not this is a good idea. The first time I read about bootstrapping, and then the subsequent 9 times I read about it, I thought it was crazy, and now I really like it. So the idea is that if you're trying to figure out the distribution from which your data came, the best estimate you've actually experimentally got is your data, which sounds almost circular. But it has this interesting property that you can use the statistical properties of the data you have to figure out the statistical properties of derived parameters, which is great. And it's so let me show you how it works, because examples are good. So imagine that I did an experiment where I just measured 7 times, and for some reason, and I believe that these measurements are entirely uncorrelated, but they happen to come out in order. So I don't think this is drift. It's just, it'll help you figure out what I did with the data in the coming slides. And the colors are there because if you want to use colors to track the numbers, that might be easier. So I'm interested in the average of these numbers. So I've got the mean of these guys by symmetry has to be 4. And then I might be interested in the mean and standard deviation of these guys, so I get a number like this. And then you can decide that, so I don't know what this looks like. It might be coming out of a uniform distribution, and I don't know anything about how to do statistics correctly on uniform distributions. Right? I could go look a bunch of stuff up, but I don't really know. So I want to come up with something that's simple that I can track. So I can get out some dice, and I can just make myself a whole new data set by rolling some dice. And every time I roll a dice, I pull another number down until I've generated. So there's been some replacement. I've got 2 7s and 2 6s, but they're just coming out of this original data set. And then I can compute the mean, and that gives me 5.14. And then I can just do this a bunch. So I can just keep generating synthetic data sets, and I can look at their statistical properties. So I can just take each one of these guys, I get a mean, and actually I'm starting to see things like they're starting to repeat and all kinds of stuff. And then I can compute their mean and standard deviation. And so this gives me some sense for if I just iterate over this a bunch of times, like maybe I'll do it 10,000 times, then I'll get some distribution of output parameters. And this is a thing where I feel like I'm to the extent that my data are an estimator of the whole distribution from which they came, this thing gives me a pretty good sense for what's going on under the hood. So, and here you'll notice that I actually got almost the same answer as by doing it the normal Gaussian way. But let's try something more complicated. So here's the SEMPA phone directory. I just grabbed it, grabbed the lengths of everybody's last name. Here's a histogram. So there are a few more people with longer last names than there shouldn't be anybody with negative last names. So I know it's going to be some funny distribution. And so here's the mean standard deviation. And now I'll just bootstrap it, and I'll do get the same game. And they're actually going to kind of agree. And so that's cool. That's actually kind of nice because I've got two methods and they're doing about the same thing. But what if I take e to the name of the name length? Is that still going to be the same distribution? I can compute the mean standard deviation, okay, that's great, but I don't know, I'm not a statistician, and I would be afraid to pick a method and then hang everything on that one method. So, do you guys think this is right? Jens thinks it's right. Turns out it's actually pretty close to right. So if I bootstrap the data, I get a similar thing, but you can start to see that there's a tail out here that's starting to get pulled by, if you get too many of the long names in your synthetic data set, it starts to pull the average up. So it's kind of nice these actually wind up being about the same because I'm about to try to convince you I'm going to do something complicated. Yeah?
Quick question about this, I just don't completely get it. So, you know, for the other example, you're just rolling dice.
Yes.
What are you doing to generate people's names?
So here I've got all I have is the data I measured originally, which is 105 names or something that are in the directory. And now I'll roll the dice and just pull name lengths out of the previous data set and create another one and compute the mean. And I'll just do that a bunch and I'll get these things on the right. And yeah, so I don't have to be a statistician and I can work on data sets that might be weird. That's my option.
But if you had been a statistician, you might have thought of the central limit theorem.
Sure. Yes. Oh, but this is actually, it's easier. So if you have lower statistics, it's bootstrapping is more tempting because you can try to generate more than you ought to be able to get out of a data set. In my case, there's really fluctuating noise, so I have some data points that really pull because they were really quiet, and other data points that are basically garbage by comparison. You have to make sure that those really high quality points don't pull the whole data set, and that's part of the reason for trying to do this.
You're trying to find out if a data set belongs to the group of correct data sets?
So I'm actually going to...
Or the correct distribution of them?
So I'm going to basically take my experimental data, and I'm going to compute a fit for science, and then I'm going to bootstrap it and compute a fit, and bootstrap it and compute a fit, and then look at the distribution of fit results to generate what's coming. So I'll get there in a little couple seconds. So at the very least, I hope this was a simple thing. You've got some dice in your data, and you just do something, and you get some distribution. I claim it's more robust than normal methods against fluctuations. You can use it in statistically really weird situations, like I'm about to do, and you can attack hard systematic errors with this approach. It's hard for you to check if I did it right. It's really hard. So if you're reading a paper and like, I pulled out the bootstrap, that's great. It's hard to look. So that's part of why I'm sharing everything that I've done, is that way you can go and check it if you want. It's computationally hard, and I think that's why people weren't doing it in the 1600s. And you have to be careful that your pretty histograms don't lead you astray, because you can generate an almost arbitrarily pretty histogram by bootstrapping more. So how do I use this? One of the things that I can generate is what I call the arbitrary fit. So I generate what you really want out of the measurement, which is the force law. What is the gravitational force as a function of attractor position? That's exactly the thing that you actually want, because you can hand it to a theorist and say, this is what happened, what do you think? Instead of like, here's my parametrization and I have some result. And so this is real uncertainties on simulated data. And so these points are all fits to a piecewise linear model. So it's physics model independent. And then this is the same approach applied to something where I've injected this red force law. And so you can't really see the blue points, but there's a bunch of blue dots that live right on that thing. And the uncertainties are taken straight out of the data just by having bootstrapped. So I don't know how to go about computing all of these piecewise linear things directly, but it's straightforward with bootstrap. And then I do have to extract this Yukawa result in the end. So I do what I call the big joint fit, and it makes this conservative choice, or at least I hope it's conservative because I'm doing it. I believe it is, where I treat all of the systematic effects that I'm interested in as acting just like a Yukawa interaction. So This is the same force law I showed you a while ago. There's this alpha, the strength relative to gravity, a lambda squared, and then an exponential, and these things just roll in a bunch of thickness corrections. But they're fairly weak functions of lambda. And then there's this B, which is if I've got some systematic effect, like a magnetic field, I can apply that magnetic field or not, and then the joint that will split this effect away from gravity in one giant fit. And then I also include a linear drift term, or not a drift term, just whether or not there's some linear effect that doesn't care about the proximity of these two masses. So there are 11 fit parameters and about 3,000 total measurements. And Jason and Nikolai have been a super big help in figuring out how I should go through all of this stuff. And yeah, John Lee also helped a bunch in verifying that I've done all the calculations right. And so this is interesting, but I can do something even more cool. I can propagate all my systematic effects. So I can, with the way I actually compute the foil displacement is with one of these arbitrary fits. And then I can correct for every bootstrap fit. I can just take a different one of these bootstrapped fits and put it in to correct for how well I've resolved the foil's motion. And this is a really hard thing to do, that I've done something complicated to figure out what the foil's actually doing. And then I need to take that uncertainty and propagate it forward to make sure that if there's too much uncertainty in this, it needs to blow up my overall uncertainty. And I could never do this if I didn't have this technique. And then there's also the fact that I have some systematic position error, that I don't know exactly how close things are together, and there's statistical and systematic noise. And it's for every bootstrap of the fit, I can just displace them by some random amount that's the size of my systematic error. And I don't know how many of you guys have done horizontal error bars in a fit, but it's hard, and to do systematic horizontal error bars is even harder, and this just does it, which is great. You guys all look convinced. So, getting closer to the measurement now. This I think may be able to answer your question. So this is what the raw outputs of my fit will look like. So I'm interested in results in the alpha lambda plane, and there's all the plots I've shown you before were the absolute value of alpha, because we don't know whether gravity should be stronger or weaker, and if you want to compare experiments with one plot, you should just use the absolute value, as long as nobody sees anything. But if you're in the business